study of chemical trails across the southeast pertaining to the early morning hours on January 31st of 2025. Now, this video is going to be a little bit different in the sense that, well, I'm talking in this one, and we're going to resort back to doing a little more of some case-by-case analysis and proving to you the level in which these trails are being sprayed, what it's doing at altering our jet stream, and what it's doing for the desired result in the weather that occurred on this date. So I'm going to try my best to include all audiences on this. Now, I will be honest, I'm going to get pretty technical to an extent, and this is going to be a little bit more catered towards an academic conversation. Now, this doesn't mean if you're someone who's a weather enthusiast or who's very interested in this topic can't follow along. I'm going to try to make it as easy as you can to follow along, but we've got a little bit to dissect here, so let's see how long this video will take here. And without further ado, before I jump in here and show you the absolute trashing and mess of these trails that were deployed, we have to set the stage and understand first what clouds do on our radiational budget. And these two schematics here that I've had pulled up for about 2 minutes now, we're looking at solar radiation. So on the left here, this is simply energy and heat that we get from the sun. Now, some of this comes in and it hits the surface of the Earth. Here's our surface of the Earth. And our Earth absorbs some of this heat, and some of this gets reflected back. Now, if there's clouds sitting up here, some of this will hit the cloud and reflect off that cloud. Some of this radiation, heat, solar energy, bounces off that cloud, and some of it will still be able to pass through that cloud and reach the surface of the Earth. Now, the amount or the percentage depends a little bit. Obviously, how dark is that cloud? That would be a matter of a surface albedo. So if you have a darker cloud, that's going to absorb more of that sunlight versus something that's more white, or a lighter colored cloud that's going to reflect more than absorb. So there is a little bit of an art to that as well with some of these clouds. And let's look at this a little bit closer here at the Earth's radiational budget. Now, this is what I was just talking about. These yellows here, this is our sunlight energy. So some of that sunlight is going to come through, burn through those clouds and reach the Earth's surface. Some of that is going to reflect back out. It's just not going to make it to the surface of the Earth. And then also, some of this will also reflect off the surface of the Earth. So not all the radiation or the sunlight and energy that reach the Earth's surface is even going to reach the surface or be absorbed. Now let's take a look at the case of what happens once this radiation or this energy reaches the surface of the Earth. What happens is some of this does try to exit back out, but these clouds will actually insulate it, and it gets blocked back inwards. Some of this also, notice, it does escape through those clouds. So having a budget and a presence of clouds is huge on our diurnal variation in temperatures, which is simply our high temperature throughout the day and our low temperature throughout the day. Now, the time of the day that these clouds are sprayed is going to have an impact. So let's break this down into two cases, because the case we're looking at is going to be more so during the PM hours or the overnight, where we have the moon. Okay, we do not have the sun, and I'll go through the case of during the daytime if we're spraying, but I won't spend as much time on that because we're more focused on this application of spraying during the overnight. So let's say we're spraying during the daytime. And here's the surface of our Earth. There is no clouds. All we have up here is going to be very small particulates of ozone and other pollutants here. That's really about the only thing that some of this sunlight is going to be able to latch onto and absorb or reflect. So for the most part, most of this energy is getting to the surface of the Earth. Okay? Now, in the case where we have clouds, that's going to alter things a little bit. So let's say we have a big cumulus cloud sitting right here. Some of this is going to get reflected back out, and some of this is going to reach that surface of the Earth. Now, what we can decipher here is, had this cloud not been here, there would not be a source of energy or heat for this to latch onto. So there is no additional external heat in the upper levels of the atmosphere during the daytime. So when you're spraying throughout the daytime, instead of reaching this energy to the surface, some of these get absorbed up into the clouds. Now, in the case where you're spraying during the overnight, this has an opposite effect. If we have a very strong cloud layer during the overnight, again, we got no sun out here. Here's the surface of the Earth. Now, from all the heating that we were subject to throughout the day, a lot of that heat that heated this surface, it's going to struggle to get out. Some of this will get absorbed into the cloud. A lot of this, the majority of this, is going to get shot back down to the surface of the Earth. Think of this cloud here as a big insulator. It's a big, warm, fuzzy blanket. It's going to help to trap and keep heat in during the nighttime. This is a case where these clouds are going to help keep long-wave radiation, which is the Earth's energy. It's going to keep it locked in towards the surface and the lower levels of the atmosphere. Whereas, let's again take the opposite of this. If we did not have that cloud there, then at night, a lot of that heat is going to be lost. It's just going to get out. It's going to leave the atmosphere, and it's going to cool rapidly. That's why, ladies and gentlemen, in the deserts, we can get highs of up to 100 degrees. And at night, we can see temperatures go all the way down to 40. There's not a lot of moisture. There's no cloud cover. And that energy, it just escapes. So putting these clouds, spraying and seeding and putting chemical trails down at certain times of the day has a desired impact and effect on our solar radiational budget and our long wave and Earth's radiational budget. So keep that in mind. Now we're going to go ahead and finally get into the meat and potatoes of this. I'm going to show you guys the entire operation of these chemical trails. What we're looking for is going to be focusing towards the Florida Peninsula, southern Georgia, southern Alabama, Mississippi, as well as Louisiana. These areas are where the spraying is most pronounced, and even within that, we see it pop up the most across Florida and the Gulf of Mexico here. Now, what you're wondering is, how can we tell that these are chemical trails and these are laid down here? These aren't plain contrails. Well, these show up at a certain level in the atmosphere, and in this case, we're looking at the long-wave infrared radiation down here. So we're looking at long-wave infrared, and these whites that show up, we're looking at cloud top height temperatures. So anywhere where we see these yellows and these oranges, this is cold. And if it's very cold, that means we're getting a cloud top height that's being recorded up where it's really cold. Let's say negative 35 degrees Celsius or so. This would be telling me roughly that we have higher cloud top heights. In this case here, the whites represent a little bit lower of a level in the atmosphere. In this case, where we see these whites show up, this is roughly speaking anywhere from about negative 8 degrees Celsius all the way down to about negative 16 degrees Celsius. This is very important. Remember this. This is the level, the temperature with height that these are being sprayed at is about negative 8 to negative 16 degrees Celsius. That will correlate to roughly 4.5 kilometers high in altitude, for reference. Okay, these are being sprayed at about this height with temperatures at about that level. Here's just another overlay. I'm looking at the ozone, so this can help sift out a little bit of some aerosol content within these clouds, and sure enough, we do see these show up. And again, I want you guys to think about working in the back of your mind. Had these trails not been here, had this not been here, there is not an additional vector for energy and heat and water vapor in of itself to latch onto these clouds. So we don't have a displacement of energy and heat being sourced into these clouds had there not been any clouds there to begin with. So adding these clouds here is diverting some energy and heat into these clouds here, and this has a big impact on the entire system, on this entire low pressure system that I'm about to get into here in just a second. Now I'm just going to show you guys a couple more frames of what this looks like throughout the day, and we switch over to the nighttime microphysics. Again, these show up as more of these darker hues, black colors, grayish colors. Those are our chemical trails, most prominent across the Florida-Georgia border, as well as really across just the northern part of Florida. That's really the hot spot with where these are all being sprayed and laid down here during those afternoon hours, early morning hours of January 31st here. Here it is zoomed out a little bit more. I'm going to show you guys again with this. We see a lot of the seeding is rooted back here across the panhandle of Florida. It goes back towards Louisiana, southern Mississippi, and Alabama, and it ejects out here across the Atlantic along the coastal regions of the Carolinas. We see it's extremely prominent and it's hatch marked. You can also see that these are moving radially. They maintain their linear form. And it's just an outlet here for all this absorption to occur. We're exchanging energy and we're putting it up here at roughly 4,500 to 5,000 meters up into the atmosphere. And I want to note with this too, look at the end of this loop. Look at just how pronounced these chemical trails are. One trail starts all the way almost near West Palm Beach, and we can track it running all the way up into southern Georgia. It curves back here into Alabama. This chemtrail itself, this whole entire trail, is over 250 miles long. This is going to have a massive input and a massive impact on the weather pattern down here. We see multiple other trails that are extending hundreds of miles here, some offshore, just offshore from Georgia, extending all the way across Florida. So these have an intricate purpose. These would be rotating in a clockwise fashion. And what I'm about to interlude into next here is how this is helping to pump up a ridge out ahead of a progressing cold front. Again, here's that still shot frame. You can pause this if you want, but let's just go at it here, and we can really mark up all these spots that these have been laid down here. And keep in mind, it's not raining in these areas. This is fair skies. All your rain is back here across Louisiana and Mississippi, Alabama. It's not raining in these areas. The seeding that's laid down here, the conditions would be more like it's partly cloudy and hazy if you were to actually be underneath this environment. So I just want to point that out too. This not raining in these areas. This is more so partly cloudy skies. So let's get into now the importance of the location of these. So that also is going to matter here. What we're looking at is, first, I'm going to show you a typical pattern here of a trough and a ridge. A trough is usually associated with a low pressure system, and this upper image I'm showing up here is just a schematic for educational purposes. In this case, we have our trough right here. This is our low pressure system. I'm looking at a 500 millibar pressure chart. So this is about where airplanes do fly in our atmosphere, where those commercial airplanes do fly. And I'm showing the linkage here. This is where we have our low pressure system. Here's where we have a ridge. The H would be sitting right about here near Nevada. And the other H, the other high pressure, the other ridge is actually sitting right off to the bottom right of my screen. It'd be more so over Cuba, but there's also a high sitting here. But the point is, I'm trying to show you guys, for educational purposes, we have a very similar setup here. Here's our high pressure, here's our low pressure, here's our high pressure. We can see it lines up quite well, and we can line that up here. Here's our high, here's our low, here's our high. Keep in mind, again, we're spraying right in these areas. This is the most prominent areas where we're using our chemical trails in this particular setup. We have a storm system that's sitting across the Central Plains. This uplift right in here, this is where you're going to get all of your precipitation and all of your rainfall, and I'll show that at the end of the presentation here, what the end result is when you combine all of this together. So one thing I will point out now, let's get a little more deeper into this. This is a model run. This is looking at the European operational model run, the 500 millibar charts, valid for 6Z on Friday, January 31st. And I line these up because this is a pretty close verification. From a model perspective, the European model did fairly well, the 6Z run at this point in time. This here, this is observed. So we can see how well these two line up. So I'm just pointing that out here from a model point of view. These are lining up quite well. I also want to point out, look at the nature of the anomaly on the reds here that are just to the north of where we have sprayed our chemical trails. This is helping to pronounce the ridge. It's going to help amplify it. It's going to pump this ridge up. And when you pump this ridge up, you're going to contract the precipitation that's ongoing across the lower Ohio Valley in this scenario. So let's get into this again. This is a case of the surface analysis. Now the surface low is sitting further up near Missouri. If we go aloft 500 millibars into the atmosphere, the low is sitting a little bit further back towards Kansas. The point being here, I'm just trying to show you guys that there is a 3D component. This is looking at the surface. This is looking at 500 millibars, several hundred, really, we're talking 50, 40, 30,000 feet up into the atmosphere here. So this is, I'm just showing a vertical component with this here before I proceed and roll forward. This now is where we're going to try to combine those ideas. So I have overlaid a 500 millibar pressure chart with the satellite of day cloud phase. So let me change my color here. Red's not going to be the best bet to show on this. Here is where, again, we're spraying. We're spraying across these locations. This is the best time to see this visually throughout the loop. When we spray in these areas, all we're doing is we're going to intensify the pressure gradient on this ridge. This is going to squeeze these equal lines of pressure. It's going to squeeze these together right in here. And this is where we're getting all of our rain. This is rain. Some of these have stronger thunderstorms embedded with them at the time that this was occurring. But off to the west, we have our low pressure system that's spinning up here in a counterclockwise fashion. So you're getting compression as well on this northwest side as opposed to the southeast side. So that's why that's very important to time this correctly. If we spray these, I'll recap this again just so we can follow along. If we're spraying across these areas, consequently, what this will do it's going to help expand the ridge. That's not a good color. Let me change this. Hold on one second. It's going to help expand this ridge north, and we see that happening. Watch down here. We see this expansion of this high and the expansion of the isobars in this area. It expands this ridge north. Once this expands, it's going to cause a compaction and further intensify precipitation in these areas. This low, spinning counterclockwise, let me change our color up one more time here, guys. Our low is going to be spinning counterclockwise here, and that's also going to consequently help compact these isobars. So these two are working in tandem with each other in order to get that desired effect. So what this does is it causes A, more intense precipitation across Arkansas, western Tennessee, northwest Mississippi, and B, had this not been sprayed here, what would have happened instead, so let's pretend like we did not spray here. What would happen instead is we wouldn't see as big of a compaction in our isobars here, and we wouldn't get as strong of an uplift in the warm air sector of the ridge. So we would not get as much uplift here out ahead of this for this incoming rain to come in. There would just be less of a compaction here. So instead of having more intense and compressed precipitation, this precipitation would be a little bit less intense, but it would be more widespread. So I'm going to repeat that again. The chemtrails that were sprayed here allowed for a further intensification and a more narrowing of banded precipitation. Had they not been there, the precipitation, the same water vapor, the same precipitation would still be there. It would just cover a more extensive area. It wouldn't be as compressed. Okay? So let's go through and roll through again with the temperature correlation on this. Here is the long wave infrared radiation. We're looking at the temperatures of those cloud top heights. And here is the negative 15 degrees Celsius layer. We see that shows up at about the yellow and pink hues. And this is where the visualization does the speaking for itself, guys. You can see that these are, in fact, being sprayed at this level of about just under negative 15 degrees Celsius. So the next thing you're going to piece together with this is, okay, well, how high up exactly is negative 15 degrees Celsius in the atmosphere? That can change. It's a hydrostatic equation that can change. Pressure can change with tendency on the height equation. That's something that's in meteorology. In other words, you're not always going to get negative 15 degrees Celsius at, let's say, 5,000 meters in the atmosphere. You can get negative 15 degrees Celsius occurring at 7,000 meters, or you can get negative 15 degrees Celsius occurring at 10,000 meters. It just depends on the time of the year and the seasonality. So again, our focus is this box in here. You're going to notice with time, as this is being sprayed, these isobars are lifting north. So as these isobars, equal lines of pressure, again lift north, it's going to help compress this backside. And as this low pressure spins across the central U.S., again, it's going to compress on this side. So we're getting a big compression, getting heavier rain as the result here for spraying these in this location. One more time, because I have to be pretty stingy about this. I have to just reiterate this over and over again. Here we're looking at the low-level water vapor imagery, and we can see this has an anomaly showing up on the low-level water vapor. Let me switch back into red. We see these areas here. They are initially showing up at this area, and we see they rise up into the atmosphere all the way up to about 30 degrees Celsius. So these are principally being laid down at that level. So let's get into this. I'll get this 1 second. Again, one more verification. Here's mid-level water vapor imagery. Again, we can see that, yes, in the previous slide, these are being sprayed at about negative 12, negative 15 Celsius, and we see that they do rise up in the atmosphere. They rise all the way up here towards negative 30 degrees Celsius. That's very important with what I'm going to show once we get into atmospheric soundings. Here's the last one. I'm pulling this and showing you again, yes, the level in which these are occurring, the cloud, the boundary layer, at least the cloud deck, the LCL, in which the clouds are showing up. It is roughly in this orange color, which is 5,075 meters approximately. And we see that these do rise all the way up to almost 10,000 meters here. The white is 20,000 meters. We don't see that shown on any of these because no cloud top heights are reaching 20,000 meters. The most focused area we pay attention on is going to be across these areas right in here. So let me go ahead and play the loop on this, and we can see that working in motion here. So again, we can see that the lowest layer of these is occurring near 5,000 meters, and it does rise up embedded within these trails to roughly that 9,000 to 10,000 meters. Here's the last part, guys. I will probably lose some of you. This is getting really into the weeds here with meteorology. This is definitely more catered towards meteorologists. But let's see what I can do here. Try to help have you guys follow along. We're looking at a skew-T diagram. And this diagram is an atmospheric sounding from Jacksonville, Florida. So we're looking, my goodness, these colors. Okay. We're looking right here towards Jacksonville, Florida. That's where this sounding is pulled from. And you put a balloon, it goes all the way up into the atmosphere, 12 kilometers up plus, and we're pulling moisture and temperature. The green is your moisture, your available moisture. It's your dew point. Your red is your temperature. And I'm trying to show you the level in which we see most saturation. So the closer we see this green line come into the red line, the better saturation we see. So in this scale from bottom to top, so on our y-axis here, this is height. The further up we are, that's higher altitude. This is 1,000 millibars in pressure. That's the surface. Our temperature is actually on a slanted axis like this. So this is where it gets pretty confusing very quickly with this. So I don't want to get horribly technical with this. But what I'm trying to show you is at 7 in the morning, the layer is at negative 10 degrees Celsius, where we see the most saturation. And that verifies with where we see the cloud top heights showing up here. It has to show up at this level on upwards, because if notice below this yellow line, look at how far away the green line is from the red line. We don't have a lot of saturation, so it's going to be hard to get clouds to form here. So the only possible area that we in fact see this layering occurring is at about negative 10 degrees Celsius, which again is occurring here at roughly 650 millibars of atmospheric pressure, which in this case, I'm roughly eyeballing this, guys. This would be about 4.8 kilometers high to about 5.2 kilometers. So roughly 5 kilometers up into the atmosphere. Now, here's that same sounding 12 hours in advance, and we see that this yellow line I drew, it rises. It goes higher up by a scale of probably about 75 millibars. It's very subtle. But my point being with this is I'm trying to show you the most saturated layer that those contrails show up. They lift north. It lifts north with time, and that's going to attach warm air advection and energy with it. So we're also pulling that energy, that addition water vapor and energy that's now up in those clouds gets pulled north. That absorption and that heat is now up in the 500 millibar level that I've marked here, and that's marching north. So in essence, guys, this here is a verification. I'm just showing you meteorologically, this is a verification here that's showing you that these are at that level. Yes, we can get contrails to form here, but I'm telling you that these are chemical trails. And this is what they're consequently doing at modifying and enhancing this weather pattern. Here's my final frames, final few things I'm going to show you. This is what it does. So we sprayed right in these areas. We have our low pressure system intensifying here across the central plains. It's going to help draw in the air this way. If we spray our chemical trails in this area, it's going to help pump up this ridge. It's going to lift this north. This energy absorption helps lift this up north. What that does is it has a compaction, and now we're getting heavier rain here across these locations. It's timed and it's deliberate. Had this not been here, instead of seeing a skinnier line of storms, perhaps it might be a little bit wider. It might look something a little more like this. So notice our scale of our width here. I would probably call this is about 200 miles here, as opposed to a case of, you're ranging anywhere from about 150 to 75 miles in thickness here. So these chemtrails, what they have done is they've caused a compaction in our pressure. They've pronounced the warm air advection in these locations across the Carolinas. And what that does, again, I can't stress this enough, is it helps intensify our precipitation that's working in tandem with this low, wrapping around and forcing dry, stabilized air on the backside of the front. Guys, that's all I have for this. I really enjoy doing some of these. This is definitely some of the most labor-intensive analysis that I have shown you with chemical trails, but, you get a little bit tired of dealing with trolls and people that just, they can't comprehend this stuff. So this is what we're dealing with in 2025. It modifies our day-to-day weather systems. It's very frustrating. It's laborious on a forecaster. And as I've said, some meteorologists, the very good ones, not that I'm trying to pat myself on the back here, but the good ones that are with it are going to know this. They're aware of this, and they forecast around it. A lot of the novice and really earlier meteorologists, they're not going to really understand some of this. If you've been taught solar radiation budgets, you need to apply that knowledge to this here, to other meteorologists. That's my word of advice to you. The first thing you got to start looking at is how clouds are going to impact stable atmospheres. If you have a conditionally stable atmosphere, a conditionally unstable atmosphere, these have huge implications on modifying our upper level jets, as well as creation and ignition of starting thunderstorms and manipulating their intensity. Chemtrails are real, they're present, and they've been here, guys, for several decades. And I'm just trying to show you in real time an application to what these do to our everyday patterns. Thanks for watching. Please share this kind of information. Very important that we're up to date on what's really going on out here with the weather. No one's going to talk about this on TV. I don't think anyone's looking to flip on the news station and listen to your local hometown meteorologist talk about how chemtrails are modifying your weather pattern, because they're not paid to do that. They're paid to just give you the weather. So there's a difference with this, guys, and I'm just bringing light out towards that. So take care, God bless, and we will for sure chat soon.